This episode is brought to you by Brilliant. Some say the world will end in fire, some say in ice. From what I've tasted of desire, I hoard with those who favor fire. Welcome to Science and Futurism with Isaac Arthur as we celebrate our 300th episode and take a look at how the Earth might come to an end, and we will be covering a range of options from natural to artificial, near-term to far future, fiery to frozen. There are a lot of options, and this channel is not noted for any compulsion for brevity, especially for our 300th episode special, so we'll be here for a bit and grabbing a drink and a snack is advised. Fiery and frozen endings are probably the two most popular end-of-the-world scenarios for contemplation, and we open the episode with a quotation from famous poet Robert Frost's classic Fire and Ice. And for anyone who's curious, Robert Frost is my favorite poet, and Fire and Ice one of my favorites by him. There's two reported inspirations for the poem, one being Dante's Inferno, and the other being a conversation Frost had with an astronomer about the sun exploding or extinguishing. Now that poem was written back in 1920, and a popular notion for the fate of stars at the time was that they were hot for the same reason planetary cores are hot. They heated under immense gravity of their own formation and have been slowly cooling. Such being the case, stars would die off by slowly cooling and dimming, and worlds about them by freezing. Another notion that sometimes made the rounds was that there was a limit how many times a planet could make the rounds of its star, that its orbit would eventually decay from friction with gas and dust and perturbation from other planets. In such a scenario, the planet falls into the sun for a rather fiery death. Later we found out their heat was being replenished by the process of fusion, and that for most stars, as that fuel runs out, they expand and burn their inner solar system, and our knowledge of that has been improved and corrected upon since, and we will discuss it as one option today. And I do mean option, because as we will see today, even if the current modern theory is correct, there are several other competing options and scenarios for ending Earth in whole or part. But while the notion of gravitationally heated and slowly cooling stars was one of the first serious scientific stabs at the end of the world, it's long been a topic of philosophical and theological discussions. We will not be discussing theology today, but it is always striking how often various end-of-the-world scenarios suggested by science, and folks worry over the most, seem to line up with those we find in various religions, mythologies, and folklore. Whether it's prophetic or gives an insight into human psychology, I obviously can't say, but as we go through the options today that represent fiery or frozen ends, or which resemble some other apocalyptic scenario like grey goo self-replicating robots being analogous to a swarm of locusts, we should keep in mind that which end-of-the-world scenario is most poetic is probably not relevant to which is most accurate. The other thing to keep in mind is that the end of the Earth is not synonymous with the end of humanity. Humanity might venture out to other worlds and burn Earth to ashes with our rocket flames, metaphorically or literally. So too, a virus might wipe out every human, or an artificial intelligence might, while leaving Earth otherwise untouched. For today though, we will speak to both options, end of Earth and end of humanity, and at times use them interchangeably, though planet or biosphere wrecking events are our main focus. Indeed, we can have multiple endings in this context, as a planet whose biosphere was obliterated to the point only a few bacteria remained might be fully rejuvenated in a billion years, just in time for the oceans to boil off into space. We've got nuclear war and nuclear winter to consider, global warming and global cooling. We have grey goo, planetary disassembly for building materials, planetary self-sentience, consumption by a black hole in our core, or freezing if a black hole got into our sun's core, or a black hole or some other large body perturbed Earth's orbit and ejected us from the solar system. We've got a warming sun boiling off our oceans and atmospheres in a billion years or so, or an expanding sun swallowing our planet in a few billion more. We've got collisions with other planets or even our own moon dropping on us, in a reverse version of the event we think scattered the debris that our moon eventually formed from. We have artificial scenarios to extend us past these, like re-terraforming our planet if we sterilized it with nukes, warming or cooling it with solar mirrors and shades if it boiled or froze, moving away from our sun if we needed to as the sun aged, or refueling or filtering our sun to extend its own life, or afterlife if we're huddling around the dying embers of a white dwarf once our sun truly runs out of fuel. We are mostly going to skim the topics of global warming or cooling from short-term or human sources in terms of carbon dioxide from factories or some volcano spewing ash out to block sunlight. There's tons of things that can alter the atmosphere's ability to absorb, reflect, or store sunlight and heat energy, natural and artificial. So even ignoring our current CO2 dilemma, we are going to need to have plans and strategies for managing planetary temperature in the long term. Even if we could convert to carbon neutral tomorrow, it won't eliminate scenarios like volcanoes, a comet or asteroid strike, natural solar cycles, or even warming from a nice, clean, and renewable power source like fusion, resulting in so much energy abundance and economic growth that we had to make cooling mechanisms just to handle all the waste heat from the electricity being used by trillions of folks living in environmentally sound ecologies. Some folks might argue that the natural ones like solar cycles or volcanoes need not concern us since they are natural, but personally I do not care if they are artificial or natural. Natural does not impress me. Natural is folks sitting in trees sticking berries up their noses and dying of random infections and plagues, and natural is getting your civilization wiped out by a tsunami or hurricane. So at some point we want to learn to manage the sunlight hitting our planet to curb warming or cooling, and to start controlling our weather to mitigate hurricanes and such. The easiest way to do that is with solar shades and mirrors, presumably sourced from the moon or near-Earth asteroids and placed either in orbit of Earth or at our L1 Lagrange point with the Sun, a spot about 1.5 million kilometers from Earth toward the Sun, about 1% of the distance. We've talked about this method many times, see our Power Satellites episode for how to do this and hopefully make a profit in the process, but in summary, the planet's temperature mostly depends on how much sunlight hits it, either reflecting or absorbing, and how long that heat gets retained. Move the planet further or closer to the Sun, something we'll discuss later today, and it will cool or warm respectively. But we can mimic that by having thin shiny plates either bounce some additional sunlight down to Earth or to bounce some away. We also potentially have the option of using very thin and large reflective balloons that float up high enough to keep most sunlight out, if we find that orbital mirrors are more difficult to build and maintain than currently expected, and such balloons might have some other advantages to be used in tandem with orbital mirrors. They are both conceptually simple, technologically simple too, but a pain because tons of giant mirrors can clutter your atmosphere in orbital space, requiring extra effort to navigate and keep it clear. And you also need to manufacture them and fly them up and repair or replace them, in the case of orbital mirrors. Hence we tend to like the idea of doing it from the moon, as there's tons of aluminum on the moon, which can be easily cooked and made into shiny aluminum foil and dragged into orbit. These mirrors will be our go-to for a lot of into-the-earth prevention or delaying options, so their basic function and creation bears repeating, but see that episode on Power Satellites for a more detailed dive. Ironically, they are non-optimal for dealing with one type of climate change I didn't mention, which is a nuclear winter. Any nuclear war is very likely to trash the orbital infrastructure of a planet, and a few million shredded solar mirrors, each originally a kilometer wide, is certainly not going to help the space debris issue. It's not a big long-term threat. A solar shade or mirror falling out of orbit on a planet wouldn't even be a threat to those below if it somehow didn't get shredded and burnt up in the descent, and they are easily replaced. But to have them to help correct a hypothetical nuclear winter, you would either need them at your L1 Lagrange point or need to replace the orbital ones, which might be rather hard after a massive nuclear war. Those are assumed to be rough on industries and economies. A nuclear winter is a catastrophe theorized to cause a planet to cool after an atomic war causes massive city and forest fires, injecting vast quantities of soot into the stratosphere, blocking much of the sunlight. The modeling that came up with the concept has been heavily criticized as flawed and simplistic, so there's doubt if a nuclear war would cause one, and if so to what degree. But I could easily imagine that if one did, our colonies on the moon or near-Earth asteroids might see a big power shift as they have the resources to be rebuilding that orbital infrastructure, clearing the debris of Kessler syndrome, and putting in new orbital mirrors or ones at L1. Additionally, another way we could get a nuclear winter in the future is all that orbital infrastructure getting blown to smithereens and causing a thick cloud of debris around the planet blocking light. Now, we don't have that many satellites up in modern times, but when we contemplate thousands of kilometer-wide solar collectors or space stations or space habitats, that could cause an amount of debris large enough to significantly dim incoming sunlight levels. That would be temporary but potentially very bad while it was slowly dissipating and clearing, and ironically the fastest way to clear it would be to detonate more nukes in high orbits. So there's a number of things which can cause a planet to cool, and solar mirrors are probably your go-to for fixing most of them, and solar shades for the reverse. Unnatural scenarios can include nuclear war or global warming, but can also include Kessler syndrome, which is when a bunch of high-speed orbital debris hits other orbiting objects, shredding them and causing more debris, which cascades to ruin everything up there. But that's up there, not down below on Earth, so it doesn't concern us for this episode, as even the cooling effect of such a cloud of debris will be short-term, at most decades, and civilization disrupting, not humanity ending. Of course, that could cause a snowball Earth scenario, which is when the whole planet freezes over. The initial mechanism can vary, but the idea is that Earth's temperature isn't just about how much light reaches the surface, but what happens when it gets there. If it hits a mirror, that light leaves without doing much to warm things, while if it hits a black object, it absorbs and warms things. Ice is quite reflective to light compared to water or most dirt, so the fear is that if a bit more of the planet got covered in ice, more light would reflect away without warming us as much, causing a little lower temperature, causing more ice to form and linger further from the poles, causing more cooling, and so on, cascading till the whole planet froze. We suspect this may have happened to Earth before, possibly repeatedly. Now it is also likely to be temporary, as a frozen surface wouldn't really affect volcanoes, but would kill off most plant life. With volcanoes spewing carbon dioxide every year, and very little photosynthetic life to remove that carbon dioxide from the atmosphere, the greenhouse effect would grow stronger and stronger until it reached a tipping point, whereupon the ice would start to thaw and trigger the runaway effect in reverse. So too, you're adding layers of ash and debris to the surface that are more absorptive to sunlight rather than reflective white ice. There's no rain washing ash and soot away when it's frozen. One alternative though, and which could happen at any time, is something which causes Earth to either get further from the sun or the sun to get dimmer. Indeed, the sun is actually getting brighter with time, but we could have weird scenarios like some planetoid hitting the sun that causes its upper layers to darken for a period, or a black hole meandering into the sun, or a planet or star passing too nearby to cause Earth's orbit to be disturbed, or even ejecting us into deep space. Indeed, this sort of planetary ejection is quite common, and we suspect interstellar space is littered with such ejected frozen rogue or nomad planets. This is one way the Earth could die from ice, and folks wonder how long life would last if the sun shut off or we got moved from it. The answer is actually a very long time. First, if something did magically stop our fusion in our sun's core, unlike in some films or shows suggesting this would be rapid, years or even minutes, we wouldn't notice a thing for many thousands of years, but a total shutoff of the sun, or us ejected into deep space, would still result in a long period of cooling. To begin with, the Earth has around 4 times 10 to the 30th joules of heat energy in it, which is how much energy the sun releases in about 3 hours. However, only about 2 billionth of the sun's light ever reaches Earth, so that is akin to around 600,000 years worth of solar energy on Earth. We wouldn't stay warm that long on the surface, obviously, but if you ever wonder why the Earth's core is so hot, it's a mixture of all the heat energy of its formation and all the nuclear decay of bits of uranium down there that leaks out very slowly at a rate of about 50 terawatts for the whole planet, or a tenth of a watt per square meter. And this process of cooling slows over time. You lose heat more rapidly when hot and more slowly as you cool. This is important as the Earth currently radiates around 5,000 times more energy from its surface than it's coming up from below as geothermal heat, varying a bit by time of day and year and location. It penetrates very little. It would freeze pretty quickly. We anticipate the oceans freezing over in a mere 2 months, giving you that snowball Earth. But then as that layer of ice insulates you, the rate of cooling will slow even more. We'd expect liquid under those oceans for at least another 1,000 years, possibly much longer, and much would depend on if the moon was still tidally heating us, which it would be if the sun went out, but might not be if we got ejected from the solar system. Perturbations of that type can break satellites off their primary, so the moon might spin away. We can keep going even after that, in underground caverns powered by nuclear reactors. The surface would be dark, and yet even as temperatures drop to the point that you might even get to see oxygen and nitrogen raining down as liquids, a kilometer or 2 down would still probably be livable. In such a scenario, you could keep retreating ever deeper to the extent of your ability to reinforce and shore up tunnels. See our Subterranean Civilizations episode for discussion of that. It also won't cool completely. It would stop at the point that the surface was radiating heat at the same rate geothermal was working its way up from the deep. Again, around a tenth of a watt per square meter, or about 5,000 times less than now, and blackbody emission of light from hot objects, or cold ones, goes up with a fourth power of temperature. Unfortunately, that would be around 8 Kelvin, considerably colder than even Pluto. But we have discussed plenty of ways to inhabit such frozen worlds before, and accomplishing them on Earth would be easier given that all our industry is already here. Realistically though, you would have to work very hard to get as many nuclear power plants going as possible, and locating all your good uranium and thorium deposits, then hole up in caverns you further insulated like thermos bottles to provide warmth and artificial sunlight for flora and fauna. With sufficient technology and hard work, a civilization could thrive on such a world, so a snowball Earth is probably not the end of Earth or humanity, even if it happened tomorrow. As I mentioned though, the planet would see the seas freeze over fast, and indeed lose its atmosphere as the oxygen and nitrogen in it cooled below their boiling point and rained down on the frozen world below as the sun disappeared or darkened. Now let's contemplate the possibility of the planet losing its seas and air as time goes on and the sun brightens, not so much death by baking or asphyxiation given how slow it is, but rather death by dehydration. The sun grows brighter every year, though it is very slow and amounts to about a 10% to 25% increase in a billion years. Still, that means in about a billion years the amount of light hitting Earth at any given moment will rise from the current average of 1361 watts per square meter to about 1500 watts per square meter for a 10% increase, or 1700 for that higher 25% brightness increase amount. That's more than a trivial rise in illumination and thus temperature, akin to moving Earth about 5 to 10 million miles, or 8 to 15 million kilometers closer to the Sun. It also means a rise in certain nastier types of radiation. How much ultraviolet or UV light comes off a star, for instance, is a factor of both its total brightness and the temperature. Raising a star's brightness by 10% doesn't mean a 10% increase in harmful UV light, because the spectrum or color of any star peaks based on its temperature, so we see even more UV light as the spectral peak of the star shifts toward the blue and violet and ultraviolet. This is a blue shift of light. A cooling star incidentally would redshift, something we'll discuss today too. UV light doesn't give us suntans and sunburns. It contributes strongly to ionizing and stripping atmosphere off a planet. So too, a brighter, hotter sun is one producing more solar wind, which also strips atmospheres off planets. There are several mechanisms for atmospheric escape, and most are exacerbated by hotter, brighter, and more blue-shifted light. So as our sun grows hotter and brighter, we expect to see atmosphere depletion rise. As atmospheres deplete, the rate of depletion tends to snowball and accelerate. Now as air leaves, pressure drops, and the boiling point and evaporation point of water decreases with that. As a brief tangent into chemistry, liquids by and large cannot exist in a vacuum, just solids and gases. In many ways a liquid is just a gas being shoved together by external air pressure, and the range of temperature in which a material can exist as a liquid decreases as pressure drops. For instance, water at normal Earth air pressure exists between 0 and 100 Celsius or 32 and 212 Fahrenheit, but as pressure drops that range narrows, the boiling point going down, and by about a tenth of normal pressure you will have about half that boiling temperature to around 50 Celsius or 120 Fahrenheit. By 1% of normal pressure, it's down to boiling at 7 Celsius or 45 Fahrenheit. The reverse is true too, higher pressure, higher boiling point, and wider range of temperatures for liquid phases of materials. This is why we run steam engines and turbines under higher pressure. A higher boiling point makes for more efficient engines. Now as the air pressure drops, all that ocean beneath is going to start evaporating at lower temperatures or faster than normal, and that will not just raise humidity but should result in some of those water gas particles ionizing into hydrogen and oxygen, and as a result some oxygen loss. The hydrogen will be lost far faster than the oxygen to the forces that deplete atmospheres, so essentially you end up with ocean levels slowly dropping. Eventually your ocean disappears and the atmosphere soon follows. The worst case scenario models I've seen put this at about 500 million years ahead in our future, assuming that higher end increase in solar luminosity, and worse scenarios for atmospheric and ocean loss, and others put it at nearly the red giant phase of our sun, our next topic, but 1 to 2 billion years tends to be more in the middle of the estimates. We often see science fiction descriptions of stars going red giant and eating their worlds, wiping out the last life in seas, but in truth both would have long since gone in even the most generous scenarios. Now this is one of our easiest disaster and end-of-the-world scenarios to manage and prevent, or at least delay, It has the three-pronged advantage of being far in the future, very slow but obvious in its occurrence, and requiring no advanced technology or mega efforts to fix. When it comes to problems, low-tech and low-effort solutions are nice, and problems you can't ignore or debate but take a long time to slowly occur, like coastal erosion, tends to be the safest bets for handling. People can't stick their heads in the sand, but also have plenty of time to act. The easiest method is those solar shades we already discussed. You just slowly increase how many of them you have in orbit or the L1 Lagrange point. Incidentally, I mentioned coastal erosion as an analogy a moment ago, but we will give it an honorable mention as a doomsday option. Tidal and tectonic activity are harder to model in terms of new land area being created and old land being eroded away, but most of this planet is covered in water, and the average depth of that water is a few kilometers, whereas much less of the planet is land and very little of it is over a kilometer up. So you could easily dump that land into the oceans more evenly, submerging it all, without making your seas shallow. Weather and tides slowly remove land back into the sea, and we rely on tectonic plate collisions to make new volcanoes and mountain chains arise, to be weathered down into land masses. We shouldn't assume that is eternal, especially on other planets which might not have giant moons or giant liquid metal cores and mantles. So I could see the opposite of our sun brightening death by dehydration model, death by flood or by slow erosion anyway. Needless to say, this is easily corrected by a civilization with decent industry given how slow it is, and nor is it a threat to life existing on a planet. Or maybe it is. It is possible a planet that became nothing but ocean on its surface, with no land for kilometers down, might lose all its nutrients and marine snow with no sunlight anywhere near nutrients, and given that the scenario assumes lower tectonic and geothermal activity causing volcanoes and new land to stop appearing, even the meager life possible by deep-sea thermal vents might shrink and halt. Ditto, without a big moon, a planet might lose the tidal effects that help with these processes, and our moon is getting further away every day, and our own days longer, so death by land drowning into the seas is a possibility, and more so on other planets perhaps. Though given that the ocean would be slowly dissipating too, the dehydration option is more likely by far, I'd say. Now the sun will keep smoothly growing a little brighter every year, but eventually that gradual brightening will give way to a faster and larger inflation into a subgiant then a red giant. But even when those relative surges happen, it will be pretty slow, and billions of years from now. That red giant may well swallow Earth, but even if it only got out to Venus, it would be implausible that we could simply add enough solar shades to Earth to keep it livable. We might be able to extend the sun's own lifetime by star-lifting material to reduce its mass, and prevent or at least delay the red giant phase followed by the white dwarf phase, which we'll get to in a moment, but an alternative is just to move Earth. Now we've discussed building spaceships the size of entire planets before, or bigger, and moving at interstellar speeds. See our Planet Ships and Fleet of Stars episodes for discussion of those titanic craft. So moving a planet at less than human walking speed away from the sun to keep us cool as it brightens is not much of a stretch of imagination compared to those. Indeed, those same solar mirrors and shades we discussed before can be used in greater number, combined with gravity tractors or reflective patches on Earth or on space towers, to slowly shove the planet away using the sun's own light to power the process. Indeed, you might pack up the entire planet and move it to a new solar system whose sun is younger or had longer to live, and you might maintain our ecosystem by a long network of relays, transmitting solar power from our own ever more distant star, or stars en route to our new star, or you might use fusion. We mentioned the option for the planet dying by snowball Earth if we got ejected from the sun, but that assumes a natural act and not a technological effort. Given the energy efforts involved, we're not talking about a few thermos bottle civilizations buried kilometers below our frozen surface running on fission power plants. We might be considering a civilization running on nuclear fusion, in which case the hydrogen in our own ocean is more than sufficient to run civilizations for eons. Indeed, you could artificially light our planet as bright as the sun and as long as the sun normally would by hydrogen fusion of those oceans. Much shorter if you could only use deuterium-based fusion, which makes up only about 1 out of every 5,000 hydrogen atoms in water, but still long enough for a planet to coast into the solar system in comfort and style. You could do vastly better with a black hole, as we'll discuss in a bit, but if you need to flee your own dying sun, with decent technology and forewarning, you can make the trip. You could later return to our sun after its red giant phase, or have just moved into the Oort cloud for that, and bring back Earth to where it was and ever closer as the sun became a white dwarf and began cooling. and through use of mirrors you could keep Earth habitable around that cooling remnant for a very long time, but white dwarfs themselves are out of fuel and are simply very hot and massive, and cool very slowly even compared to planets, but they are out of fuel and they are cooling, so living around one eventually results in a death by freezing. Of course, you might be able to refuel your sun or extend its own life, and we discussed the process for that in our episode Starlifting, where by means magnetic and thermal you blow gas off your sun, pull out the elements heavier than hydrogen, which include metals and key atoms for organic life, and thousands of times more than Earth has. You then drop the hydrogen back in if you like, or keep it for other uses. Either method extends the sun's life, which stores and mixes its contents like a boiling pot, but slowly concentrates helium in the core, poisoning regular star burning of hydrogen long before it runs out of hydrogen. Indeed, we estimate our sun would only burn about 10% of its hydrogen fuel before dying. By removing the helium and heavier elements, we prevent this early natural death. What's more, as a star's mass decreases, whether by removing just those heavier elements or also the hydrogen, it burns slower and dimmer. As we've noted, the Earth only gets about a 2/1000th of the sun's emitted light, so we could dim our sun a lot by lowering its mass, extending its lifespan, and either move Earth closer or just add a lot of solar mirrors. It is also possible to take gas and fuel from other stars to bring it to our sun, removing spent fuel and adding fresh hydrogen. Indeed, most of the hydrogen in our galaxy is floating around in clouds, not other stars, but it's nicely concentrated in those stars, which also provide the power to disassemble them and hurl giant pods of hydrogen back to our solar system. In this way you could extend our sun's lifetime for untold trillions of years. On the topic of disassembly though, we probably need to acknowledge that billions of years is a long time to assume a status quo on Earth, and civilizations disassembling other stars or other planets to help build giant stellar engines, like those used for starlifting, might not consider Earth exempt from that. Or they might place special value on Earth, but find it easier to disassemble it or its biosphere for full transport to another system, like moving a house brick by brick. Earth may end simply because it's seen as more valuable for its raw materials, to humanity or to an alien invader, or some post-human replacement for us like artificial intelligence. That could happen a billion years from now, or even in just a few millennia. Of course, the end of the world might be an accident too, and even potentially in this century, and from something artificial but not intelligent. We often imagine inventing self-replicating machines and them running amok, disassembling everything to make more of themselves, and we call this a grey goo scenario. A grey goo is one way a world might be disassembled, either an accident running away on us, or an intentional effort to disassemble the world for raw materials. But ironically, grey goo, in its natural and runaway state, might not be an Earth ender, just an Earth changer. We often compare grey goo to early life, green goo, as basic microbes are essentially self-replicating machines. We might expect grey goo to evolve more complexity with time too, as green goo apparently did, even to the point of sentient and sapient life forms. However, the whole planet was not really green gooed, only a very thin film on its surface was, and this is potentially true for grey goo too. Consider, we contemplate runaway self-replicating machines turning the whole planet into more of themselves, but how could the lower layers do this? There's no place for them to absorb sunlight to power themselves, for instance, when buried under kilometers of their cousins. Presumably, regardless of the power source, they should seek to be on top getting sunlight for free energy and open air or space for easier cooling. So too, what sort of machine could really operate when buried under kilometers of other tiny machines? Surely they would be crushed and grow hot, just like our own magma. So grey goo would not get the whole planet, and indeed we likely would see slow mutation into mini-species as some specialize in focusing on getting to the surface, while others learn to cannibalize and eat their damaged cousins, slowly sinking through the sea of each other to the magma layer below. One can easily imagine much speciation and variations of our own ecosystems, including the marine snow or organic debris in our own oceans, feeding the sunless ecosystem deep down below. Here though, it's cannibals in a sea of metal and silicon, floating on a raft of wrecked and compressed predecessors, itself floating on the magma, occasionally perturbed or volcanoed to higher levels to refresh things. Nor would they be cannibals for long as they diverged much as early life did here, so in truth grey goo would only replace the green goo layer on Earth and probably just spawn a new era of life. If you want to eat even the planet's core, truly obliterate Earth, then your better bet might be a black hole, and these are an amazing power source civilizations will likely seek to master, 100 times better than even nuclear fusion, but often perceived as dangerous. However, as we saw in our episode Weaponizing Black Holes, while they're all dangerous, it really takes a precision and deliberate effort to destroy a planet with one, or better yet a pair of them, and one accidentally escaped from ground-side power plants would probably need millions of years to eat Earth if they ever could. Plus, you can actually capture and move one with sufficient effort. They really would not sink to the core of a planet till it was far too late to care, instead bouncing around inside a world. See that episode for the details. But black holes offer us one option for long-term survival that our sun's natural fate does not. First, as probably the best power source in known physics, you can slowly dump matter into them to produce power. Every kilogram of mass has the same fundamental energy in it, E equals mc squared, and you can get somewhere between a fifth to half of that energy out of a black hole by dropping into one, and the rest as very slowly released Hawking radiation long after. Any kind of matter works equally well, including your garbage or hazardous materials, or abundant hydrogen helium, or potentially even dark matter. We've mentioned losing Earth's ocean to evaporation, and they mass about a billion tons. That represents a mass energy of 10 to the 38 joules, or 100 million billion joules, which is about 10,000 years of light production for the whole sun, or 20 trillion years worth of sunlight for the entirety of Earth, which again only gets about a 2/1000th of the sun's released total sunlight. That's a very long time, and you could be feeding in mountains instead of water. Earth itself masses more than 1,000 times what our oceans do, meaning you could drip feed the whole planet into black holes to run it for quadrillions of years, long after every star in the universe had died. You might run power off one for Earth from stores of other matter too. Jupiter is around 300 times more massive than Earth, and the Sun 1,000 times more massive than Jupiter, and the galaxy a trillion times more massive than that, if you want to raid other solar systems for fuel. Including dead sources, there's no reason you can't feed even dying white dwarfs into black holes, though this is rather tricky without setting off a supernova, and far harder with a neutron star, which are even denser and require even more energy to starlift material off of. Though carefully skimming the surface off of one with a black hole is one possible approach, albeit one requiring amazing precision to avoid catastrophic explosions. So when it comes to the end of the Earth, it might be a long way off indeed, not thousands of years or even a few billion, but a billion years or more. Yet will it be by fire or ice? One might think in a universe slowly cooling off and run on scraps of power from black holes that it would be ice, but our current theory says black holes do evaporate over time and give off energy faster and faster as they get smaller and smaller, releasing ever more Hawking radiation ever more quickly, till growing to be miniature suns. In the end, if true, and if you can survive long enough to tap dying black holes for this sort of power, your ending isn't in darkness and ice, but a swelling period of ever brighter millennia and centuries, ending in an explosive surge. You would be consumed by fire if you chose to remain close, but given that there would be nothing left to live on, except maybe iron stars, countless eons beyond, there would seem little reason to escape the fire and freeze in the cold endless night beyond. So civilizations would get to pick fire or ice as they so desired, but it's a choice they need not make till a future so far ahead in time it makes a billion years seem like an eye blink. Today we are celebrating our 300th Thursday episode, and we will get to discussing that and our upcoming schedule in just a moment. But first, a common problem that comes up on this show and other science shows is always how much math to put in, because it really is often very fundamental to understanding and mastering concepts, and yet lots of folks are not comfortable with math. I try to minimize how much we put on screen because simply explaining math doesn't help much. You have to practice with it in a hands-on fashion, and that's something our friends at Brilliant focus on: interactivity. Over the last year, Brilliant has built a whole new platform for their courses that takes interactivity to the next level. Pre-algebra, mathematical fundamentals, and algorithm fundamentals are the first courses launched on this platform. Brilliant is a website and app built off this principle of interactivity. You learn best while doing and solving in real time, not by long lectures or memorizing formulas and facts. With Brilliant, you can jump right into solving problems and be coached bit by bit until before you even realize it, you've learned a new subject in STEM. And if you do get stuck or make a mistake, you can read the explanations to find out more and learn at your own pace. Brilliant has something for everybody, whether you want to start at the basics of math, science, and computer science, or try any of their many excellent daily challenges. And if you'd like to join me and a community of 8 million learners and educators today, click the link in the episode description down below or visit brilliant.org/IsaacArthur. So as mentioned, this is episode 300, and as I've explained in the past, that is a somewhat debatable number because we didn't start doing weekly episodes until about our 20th, and the formal numbering system has actually become the production week these days, so that the 300 does not include any of the bonus episodes we've done, which when combined with live streams and two-part collaborations puts us at nearly 400 episodes, not 300. Amusingly, it's 357 weeks since the very first episode, and this episode comes out exactly 2,500 days after the original episode came out, which somehow seems the better benchmark. Nonetheless, since we started doing them weekly, we have never missed a single Thursday release. Not 1 week, not even on my honeymoon. I occasionally think about resetting the numbering in some fashion, but the problem is, my own calendar of personal tasks and even my journal use this numbering these days, which is pretty indicative of how much the show has grown over years from a casual experiment to a major hobby to a full-time plus profession, and it's a great chance to once again thank all the folks who have helped the show grow. Every volunteer who's helped with the script editing, or making animations or moderating our social media forums, every Patreon and Nebula subscriber, PayPal or snail mail donor, super chatter in the livestream, and our sponsors, and every person who's watched episodes and shared them with others, hit that like button, left a comment, and subscribed to the show. Without you, this show wouldn't be possible, and I cannot thank you enough. I've also gotten married since our last benchmark of 200 episodes, which came out about the same time Sarah and I started dating, and I can't thank her enough for her help on the show, including co-hosting our monthly livestream, and putting up with the long hours I spend writing and producing episodes. So again, thanks to everyone, and here's to 300 more episodes, 2,500 more days of production, and one more great week. Speaking of live streams, we will be having one this weekend on Sunday, July 25th at 4 PM Eastern Time. Then we will close the month out with a third episode of our Galactic Domination series, The Galactic Laboratory. That will take us into August, which we will begin with a look at whether or not it's time for us to embrace nuclear power, and the week after that we'll look at what the next space station after the ISS will be, before we have our mid-month Sci-Fi Sunday episode, Alien Artifacts and Xenoarchaeology, on August 15th. If you want to know us when those and other episodes come out, make sure to subscribe to the channel, and if you'd like to help support future episodes, you can donate to us on Patreon or on our website, isaacarthur.net, which I'll link in the episode description below, along with all of our various social media forums, where you can get updates and chat with others about the concepts in the episodes and many other futuristic ideas. You can also follow us on iTunes, SoundCloud, or Spotify to get our audio-only versions of the show. Until next time, thanks for watching, and have a great week.